This video starts the consideration of chemical bonding, or how atoms hook up together. Turns out that that's really important in understanding most of what happens in chemistry. So to begin thinking about that, we need to think about something called valence electrons, which we've already talked about, and the Octet Rule. So back in the early 1900s, 1902, a scientist by the name of Gilbert Newton Lewis was trying to teach some of his beginning chemistry students, about the periodic table. And he came up with the idea that you could explain a lot of the observed chemistry at the time by making note of this important fact that is called the Octet Rule. Gilbert noticed that many main group elements tend to gain or lose electrons, so that they end up with 8 electrons in their outer shell. Now at the time, the shell model hadn't really been invented. In fact, Gilbert proposed this only a couple of years after the electron had been discovered, and 9 years or so before they even knew that the atom had a nucleus in the center. And quantum mechanics, quantum theory, was still just not really developed yet. So this was really an impressive accomplishment. So Gilbert was able to, looking at chemical behavior, come up with the idea that you could think of these electrons as being on the outside of the atom. And because these electrons are responsible for bonding, he called them valence electrons. Because back in the old days, chemists knew about how many attachments an atom will typically make to other atoms, how many bonds an atom makes to other atoms, and they called that the valence. So valence is the number of atoms that an atom will connect to. And so he started calling these things valence electrons, even though he didn't really know about shells and all this kind of stuff. And it turns out that the Octet Rule is still pretty important in thinking about bonding. So let's define what valence electrons are. So valence electrons are typically defined as the number of electrons in the outer shell of an atom. And being the outer electrons, it makes sense that these would be the electrons that are going to be involved in bonding to other atoms. These are also the electrons that are most easily lost, or if we add an electron to an atom, that's where the electron is going to go, in the outer shell, sometimes called the valence shell. So valence electrons then are the electrons that are most easily removed. So if you remember AVEE, the concept of AVEE from the last chapter, we remember that there was a pattern. So let me sketch out a little periodic table here. So here's a periodic table, and what we remember is that AVEE increases as you go up to this corner of the periodic table. So AVEE is big up here and small down here. AVE measures how tightly an atom will hold on to its valence electrons. So the atoms that are up here in this corner of the periodic table hold on to their valence electrons really tightly and are going to tend not to lose them. And instead they're going to tend to gain electrons. So it's a strong enough pull that if an electron happens to drift into the valence shell, these elements are going to tend to gain electrons. And so if they gain electrons, they're going to pick up a negative charge, and so they're going to form anions. And you'll notice that this corner of the periodic table is where we have the nonmetals. So nonmetals are going to be the atoms on the periodic table that tend to gain electrons and form anions. Over here on this corner, the AVEE is small, so it's easy for those electrons to lose some of their valence electrons. And if they're losing an electron, then what's left behind are the remaining electrons and the nucleus. But the nucleus has a certain number of protons, and now the number of protons exceeds the number of electrons, so it's going to become a positively charged ion that we call a cation. So let's write down a more specific definition for how we can figure out how many valence electrons an atom has. So the valence electrons will be the number of electrons past the previous noble gas, but we're going to omit any filled D or F subshells. Alright, so this is our route for calculating the number of valence electrons that a particular atom has. So let's do that for an atom. Let's look at fluorine. And so we need to write down the electron configuration of fluorine. So if we look at a periodic table and we find the noble gas just before fluorine, that would be helium. So fluorine's electron configuration is the same as that of helium. Then it's going to be 2s2, 2p5. So the outer shell electrons, the valence electrons, are the ones that are past the previous noble gas, so we're not going to count any electrons that are here in the noble gas core. We're just going to look at these guys. And if there were any filled D or F subshells, we would leave those out. So here I've got S and P subshells, so I'm going to count those. So I've got 2 plus 5 electrons. That gives me 7 valence electrons for fluorine. And you'll remember we saw a pattern for the main group elements, so not the transition metals, but the main group elements on the left and the right, that the group number, the Roman numeral group number, is equal to the number of valence electrons that that atom has. So that's a quick way to figure out the valence electrons. Let's look at a slightly more complicated example. Let's look at vanadium. So vanadium has the electron configuration that's the same as argon, and then working our way across the periodic table, it would be 4s2, 3d3. So in this case, our outer shell is the 4s shell, but we're going to count these 3d electrons as well because it's not yet filled. We only omit them if they are filled. So we're going to have 2 plus 3 electrons. For vanadium, we would expect to have 5 valence electrons. So vanadium could easily lose up to 5 electrons. Of course, it gets harder and harder to take those electrons off, so losing all 5 would be unlikely. Let's do a yet more challenging example. Let's look at an element like tin. So tin has the same electron configuration as krypton, so that's the previous noble gas. And then looking down, tin is in row 5 of the periodic table, so we're going to start with 5s2. Then we work our way across the D block, so we've got 4d10, counting our way across. And then we enter the P block, so we're at 5p. And then 10 is the second element across the P block, so it's going to be a 5p2. So in this case, we're going to, because we have a completely filled D shell, we will typically omit that D shell and just count the S subshell and the P subshell. So we've got 2 electrons in each of those. So we would say that 10 has 4 valence electrons. And similarly, we're going to omit electrons that are in a completely filled F subshell as well. So if we look at an element like lead, Pb, lead has the same electron configuration as the previous noble gas, xenon. And then we work our way across. So starting on the 6th row of the periodic table, we've got 6s2, 4f14, 5d10, and 6p2. So again, we're going to omit the completely filled F and the completely filled D, and just count that we've got these 2 here. So again, lead is going to have 4 valence electrons. And that's consistent with the position of both tin and lead in group 4A on the periodic table. So group 4A, carbon, silicon, germanium, tin, and lead all have 4 valence electrons. So that's how we count and figure out the number of valence electrons that we have. Now, another helpful idea that Lewis proposed and was subsequently modified is representing the valence electrons by something that has been named in honor of him, called a Lewis dot symbol. So what we do with a Lewis dot symbol, let's just write down the Lewis dot symbol for carbon as an example. So carbon has the same electron configuration as helium, then it's 2s2, 2p2. So carbon has 4 valence electrons, right? 2 plus 2. All right, so a Lewis dot symbol, what we're going to do is draw the symbol for the element. And then we're going to think of that there are 4 spaces around a symbol, top, bottom, left, right. And each one of those spaces can hold a pair of electrons. Now sometimes we will see symbols where we have to take up more spaces, in which case we can start using the corners as well. But the idea is that we want to put electrons in these spaces. So what we're going to do for carbon is we start off and we put 1 electron, we're going to represent that as a dot, in each one of these spaces. Now, once we have put 1 dot in each space, then we would go back and start adding more dots to each space until we have 2 in each space. So each space, like this space up here, can hold at most 2 electrons. So electron pairs are very important in Lewis's model, and so we're going to always want to keep electron either in 1s or 2s. So we're never going to group them together in groups of 3 or 4 or something like that. So this would be the Lewis dot symbol for carbon. So if we look at something like oxygen, oxygen from the periodic table has 6 valence electrons. So we draw the elemental symbol for oxygen. We start putting our electrons around 1, 2, 3, 4. Then we need to pair 1 up, 5, and pair 1 up here, 6. So this is a possible Lewis dot symbol for oxygen. By the way, it doesn't matter if you rearrange the electrons to look like this. That's still perfectly okay in terms of a valid Lewis dot symbol. So where these dots occur doesn't matter. It does matter that you have them grouped in 1s and 2s. So this would be an incorrect Lewis dot symbol, even though it shows 6 electrons. So we don't do that. So Lewis dot symbols will be very useful to us later when we begin thinking about electrons being lost or gained to form compounds. Let's look at a simple example. We're going to look at sodium. So the Lewis dot symbol for sodium, sodium has just 1 valence electron, so I'm going to put a dot there. we're going to look at the atom chlorine. Chlorine has 7 valence electrons, so 1, 2, 3, 4, 5, 6, 7. Now, chlorine is on the right-hand side of the periodic table, so it exerts a really strong pull on electrons. Sodium is on the left side of the periodic table. Its AVEE is low, so it exerts a weak pull on its valence electrons. So what happens is if this electron on sodium happens to find its way into the valence shell of chlorine right here, because maybe these atoms bump into each other, then it's going to end up sticking there. And we can imagine that we form this situation. So we have a sodium, but it's lost an electron, so it's now positively charged. And then we have a chlorine atom now with 8 valence electrons in its outer shell instead of the normal 7. So if that's the case, then this guy has picked up a negative charge. And so we're going to draw brackets around here, and as a superscript, we're going to write the charge so that it's easy to tell without having to count and compare that this is a negatively charged ion. And so we've made ions in this fashion, and we can imagine then, because of Coulomb's law, that the positive charge likes the negative charge, and these guys stick together with a Coulombic electrostatic force, and bing bada boom, we have made an ionic compound. 2 charges, a cation and an anion, just like that. So the Lewis model helps us out a lot when we're thinking about all these different kinds of bonding. So in the next video, we're going to turn our attention to looking at how atoms can share electrons to complete their octets. So notice that when we did this example here for sodium chloride, that sodium lost an electron, so now it has a complete closed shell noble gas configuration of electrons, right? Its outer shell is now filled because it lost an electron. Similarly, chlorine's outer shell is now filled because it has gained an electron. So this follows Lewis's octet rule. But there may be other ways for atoms to gain and lose electrons, say by sharing electrons. And that's a special type of bonding that we're going to talk about next called covalent bonding.